Welcome to Chem 1A at Shasta College. This is the first Chapter 3 screencast, and it is an introduction to chemical moles and formulas. If you were a cook or a baker making food for lots and lots of people, you would certainly order something like eggs, not by how many individual eggs you needed, but by how many dozens of eggs you needed. And if you were an office manager, you wouldn't order how many sheets of paper you needed. You'd order paper by the ream or possibly by the box. And things like a dozen, which means 12 of course, or a ream, there's 500 pages in a ream of paper, those are useful quantities for these sorts of situations. Now, chemists of course deal with matter, the substance that makes up our world, and even very small quantities of matter, like this tiny droplet of water, contain tremendously large numbers of the particles that make it up, in this case water molecules. And because of this, chemists use a unit somewhat analogous to a dozen, and it's called the mole. Now, a dozen always means 12. You have 12 eggs, or a dozen eggs, that's 12 eggs. You have a dozen horses, that's 12 horses. And a mole is also a number of things, but it's a much, much bigger number. 1 mole of anything is 6.022 times 10 to the 23rd of those things, whatever they are. This is kind of like the chemist's dozen. Now, of course, you're typically not going to count out individual atoms or molecules or ions. We typically weigh things out, and the mole has another meaning, and the mass of a mole of any element or of any compound can be determined from atomic masses, and those are of course found on the periodic table. Now, one other thing to note, this really large number, 6.022 times 10 to the 23rd, is also called Avogadro's number, and here it's symbolized by N sub A. N stands for number, the subscript A stands for Avogadro, and the definition of Avogadro's number is how many atoms of the isotope carbon-12 are in exactly 12 grams of carbon-12. So if we were able to pile carbon-12 atoms, only the isotope carbon-12, on a scale and get it up to exactly 12 grams and then count how many atoms we have, what we would end up with is a really large number, and it's exactly, to a lot of significant figures, 6.022, 14129 times 10 to the 23rd, and we'll usually just use 6.02 or 6.022 times 10 to the 23rd for the Avogadro constant, or Avogadro's number. Now, this is usually easiest to deal with by example when starting. So let's say that we have 1 mole of copper. Just as a note, mole, M-O-L-E, our abbreviation for that is MOL. So 1 mole of copper, how many atoms is that, and how many grams is it? Well, since it's a mole, it's 6.022 times 10 to the 23rd of those things. Just like if it was a dozen, it would be 12. So 1 mole of copper is 6.022 times 10 to the 23rd copper atoms. And then the periodic table is useful because if you look where copper is on the periodic table and then look at its atomic mass, that is the mass in grams of 1 mole, or 6.022 times 10 to the 23rd, copper atoms. So notice that the 63.55 is the average atomic mass of the naturally occurring isotopes of copper, and in AMU it's the average mass of 1 atom, and in grams it's the total mass of a mole of atoms. Just for some perspective, a mole of copper is about 22 of the old pennies, the pre-1983 pennies that were pure copper. And if you weighed that, if you had 1 mole of copper, you'd get about 63.55 or so grams. And if you were able to zoom in and count the atoms, you would end up with this 6.022 times 10 to the 23rd atoms, this huge number. Okay, second example. What if we don't have exactly 1 mole? and we wanted either grams or atoms. Well, in this case, we have 0.0463 moles of krypton, and we'd like to know how many grams we have. And this is a conversion problem. But we're going to now be using the periodic table to get our information. So, usual conversion problem method, we start with the known quantity. We look for a conversion factor that will cancel out the unit that we're starting with and want to get rid of. So, moles will go on the bottom of our conversion factor. And then on the top, we need to know what the mass is. So we look on the periodic table. For krypton, the mass of 1 mole is 83.80 grams. So that goes on top. We do the math, cancel out the units, and 0.0463 times 83.80 gives us 3.88 grams of krypton. That's the mass that corresponds to that number of moles. What if we wanted atoms? Well, in this case, we actually don't need the periodic table, but we do the same type of process. We start with the known number of moles of krypton. We look for a conversion factor that converts from what we have, moles of krypton, to what we want, which is krypton atoms. And if it's a mole, it contains 6.022 times 10 to the 23rd particles. And in this case, the particles are krypton atoms. So we do our math. 0.0463 times 6.022 times 10 to the 23rd, do our unit cancellation, and we get 2.79 times 10 to the 22nd krypton atoms. So notice we have two ways of looking at the amounts, number of moles of krypton, how many grams it is, or how many atoms it is. Okay, let's do one the other direction. 2.465 grams of copper. How many moles of copper is that? Well, we start with what we know. We look up the atomic mass, which we've used previously. This time we're canceling grams, so the mass goes on the bottom and the moles goes on the top of our conversion factor. And 2.465 divided by 63.55 gives us 0.03879 moles of copper that mass is equivalent to. Now, what if instead we were trying to find number of copper atoms, starting with grams? Well, if this was the only problem we had, to convert from grams into number of atoms, we'd have to first convert from grams to moles and then from moles to atoms. But we've already done the grams to moles conversion, so let's just continue from there. We have 0.03879 moles of copper. Our conversion factor is 1 mole of copper contains 6.022 times 10 to the 23rd copper atoms. Cancel units, do the math, and we get 2.336 times 10 to the 22nd copper atoms. Now note, this mole concept, this mole idea, is very useful in lots and lots of chemistry situations. It's going to help us determine the formula of a compound and determining all exact amounts of substances that react or are produced during a chemical reaction, and lots more. So you have to get to where you're pretty able to do certainly the basic calculations and conversions readily. And here's an example of determining a chemical formula. This is actually a lab that we sometimes do in class. If you take a piece of lead, in this case it weighs 4.380 grams, cover it with lots and lots of sulfur, and then put it in the fume hood and heat it very vigorously with a Bunsen burner, and you'll do this in a crucible with the lid on. What ends up happening is a reaction takes place between the lead and the sulfur. The excess sulfur burns off, and in this case 0.678 grams of sulfur actually reacted with the 4.380 grams of lead and made a lead-sulfur compound. So a couple questions. How many moles of lead does the compound contain? How many moles of sulfur does the compound contain? And then what's the formula of this compound? Okay, so the first thing we're going to do is determine how many moles of lead the compound contains. And we start with the number of grams of lead we know we have. And we're going to want to convert this into moles. So we look on the periodic table and see that the atomic mass of lead is 207.2 grams. 1 mole of lead equals 207.2 grams of lead. We set up our conversion factor to cancel out grams of lead, and we do the calculation, and we find that this is 0.02114 moles of lead. Second part of this question, how many moles of sulfur does the compound contain? And we do this in pretty much the same way as we did the previous part of the problem, with simply we have different numbers because we have a different substance. So we have 0.678 grams of sulfur, and the atomic mass of sulfur is 32.06 grams. So 1 mole of sulfur weighs 32.06 grams. We want grams of sulfur to cancel, and when we do the math, we get 0.0211 moles of sulfur in this compound. Now you might notice something about the numbers we got for moles, and we're going to now try to find the formula of the compound. And the key idea is that if we have a compound, the ratio of the particles that make up the compound is the same as the ratio of the moles of the substances that make up the compound, and that's going to give us the chemical formula. In this case, we have lead and sulfur, which are going to be ions. It's a metal with a nonmetal. So the ratio of ions of lead to ions of sulfur is going to be the same as the ratio of moles of lead to moles of sulfur, and that's the same as the ratio in the formula. Okay, let's see how this works. Usually the easiest thing to do is to take your moles of each substance and then see what they give you for a ratio. And in this one, you have 0.02114 and 0.0211. Those are about the same number, so the ratio is going to be 1 to 1. But if you don't have an obvious ratio, it's usually good to take the bigger number, divide by the smaller number, and see what you get. And in this case, of course, you get approximately 1. Remember, we're doing an experiment, so we round off to the right number of significant figures, and we may have to kind of pay attention to the approximation. But essentially, this is a 1 mole of lead to 1 mole of sulfur ratio. Therefore, the empirical or simplest formula for this compound would be Pb1S1, and of course, we typically just write that as PbS. And the name of this would be lead 2 sulfide. Remember, sulfur is going to make the negatively 2 charged sulfide ion, and lead is not going to be too predictable what its ionic charge is, but if it's a 1 to 1 ratio, then that means that the lead has to be the +2 ion. So this is an important kind of summary concept. In any sample of a chemical compound, the mole ratio of the elements is going to be the same as the atom or potentially ion ratio of the things that make it up. And we just saw this with a 1 to 1 ratio for lead and sulfur. But if we have the compound, molecular compound C2H6O, then that's going to contain carbon, hydrogen, and oxygen in exactly a 2 to 6 to 1 ratio, both in terms of atoms and in terms of moles. Now, the last thing to do is, for this compound, we've analyzed it, we've found that its empirical formula is PbS. What's the formula mass of this compound? And then what's its mass percent lead and mass percent sulfur? Well, let's take these one by one. Formula mass is going to be the mass of that compound or that formula. And since it is made up of, for every 1 mole of lead, there's 1 mole of sulfur, and formula mass is what's the mass of 1 mole of the whole substance, then since lead is 207.2 grams for a mole, and sulfur is 32.06 grams per mole, if we add those up, and we have 1 mole of each, then we have 239.3 grams, and that is the mass of 1 mole of PbS. That's what is called the formula mass. If we're dealing with molecules, then it would be called the molecular mass. Second question, what's the mass percent of lead in this compound? And the definition of mass percent is it's the mass of the thing we're interested in this case lead, divided by the total mass, and then we multiply by 100 to get percent. So in this case, out of the 239.3 grams, that is the total mass of lead and sulfur in this compound. The mass of lead is 207.2, so we divide those and multiply by 100, and we get 86.6% lead. What's the mass percent of sulfur? Well, we would do the same thing, except we'd use sulfur. Out of the 239.3 grams of compound, 32.06 grams are sulfur. Divide that, multiply by 100, and you get 13.40% sulfur. And notice, of course, you could have probably predicted this from the previous answer. If it's 87 or 86.6% lead, then the remainder, the 13.4%, must be sulfur. And this is true in general. The mass percents of the elements that make up a compound have to add up to 100% overall. And that's it for the first Chapter 3 screencast.